Let's see, we've got one more piece of the puzzle before we can actually start doing Galois theory. And so we're starting a new chapter. This is a longer chapter than the last one. The chapter on normal extensions was actually kind of short. So now our next chapter. So, no, not chapter 5, chapter 4. All right, is separability. Separability. Okay, so we're going to start with a definition. In fact, we're going to have sort of a sequence of definitions that lead to the definition that we actually need. So first, an irreducible polynomial, say f in k bracket x, is separable over k if, well, there's a few different ways to say this, so I'll say it first like this. So if every root of f is simple, which you may or may not have heard this term simple root, that means a non-repeated root. So non-repeated. So an irreducible polynomial is separable if every root is simple. There's one way to say it. That is. So now what would this look like? Well, if you took your polynomial and you factored it in the splitting field, what you would see then is you would have distinct linear factors, right? So that is if sigma is the splitting field. Actually, any field over which, any extension over which it splits, but we'll just stick with the splitting field. So if sigma is the splitting field for f over k, then f will look like x minus alpha 1 x minus alpha n, where the alpha i's, and these are in sigma, of course. Well, let's say alpha i's are distinct. I can't spell distinct. Distinct. And here, of course, all of these alphas live in sigma. Right, so here's another way to think of it. It factors into distinct linear factors. Another way to say alternatively, f is separable. How do I say this? Oh, yeah, let's say it like this. Not alternatively either. So we'll just say so. If the degree of f equals n, then f is separable over k if and only if f has n distinct roots. So, I mean, this is a full chalkboard worth of stuff saying that we're going to be happy, we will like it, when our polynomial does not have repeated roots. Irreducible polynomial does not have repeated roots. Now, okay, so there's the first of our definitions. We can generalize this. So we'll say more generally, a polynomial f bracket x, or sorry, f in a k bracket x is separable over k if each of its irreducible factors are separable over K. In other words, or what we're doing now is we're defining separability of a polynomial that's not necessarily irreducible. How do you, or what does that mean? Factor it into the irreducible factors in K bracket X if each one of those factors is irreducible over K as defined in our original definition, then we say that the polynomial is separable. Okay. Now, so we've defined what it means for a polynomial to be separable. Now we'd like to define what an element in a field means, or what it means for an element to be separable. So we start off with an extension. So given an extension L over K and alpha in L, we say that the element alpha is separable over K. Okay, so what should this mean? Well, it should mean, or how what do we want to say here? Well, it should mean that alpha has a minimal polynomial that's separable over K. Now, to have a minimal polynomial, it needs to be algebraic, and so alpha is separable over K if two pieces to this definition. So the first part, alpha is algebraic over K, and then secondly, the minimal polynomial is separable over K. All right, and now the definition that we actually need, we had to sort of work into this. So the extension L over K is separable if every alpha in L is separable over K. So how would we put that all of this stuff together? So we're going to be interested in separable extensions, and an extension is separable if every element of the big field has a minimal polynomial that has no repeated roots. Right? So a couple of say observations. The first, so this is just built into the definition. So if L over K is separable, then L over K is algebraic. Why is that? Well, because what do we say here? It means that every element has to be separable, which means that every element has to be algebraic, right? Which means then that the extension is separable. The second observation, so if, let's say that we have a separable extension, so if this is separable, and we have some field in between, so let's say M is intermediate to K and L, then M over K is separable. So let's see, now why would that be true? Well, what we know is that every element of L is separable over K. which, because M is sitting inside L, that would tell us then that would just force every element of M to be separable over K. Now, if you compare, so we've got these two concepts. We've got normality, right? Normal extensions. Now we've got the separability, and so I don't know. By comparison. So being a normal extension is, I'll put this in quotes, is rare. I mean, what does it take to be a normal extension? Well, it essentially means it's got to be a splitting field for some collection of polynomials. In the finite degree case, it needs to be a splitting field for some polynomial, and that's, you know, I mean, that's kind of hard, right? I mean, being a splitting field is not, you know, is sort of a very not delicate. It's not the right word, but yeah, in some sense, it's delicate. So, for example, I mean, you know, this is not a very exotic extension here. So, you know, for example, right, if you look at Q adjoin, we saw this last time, Q adjoin cube root of 2 over Q is not normal. On the other hand, so we will see that separability is pretty common. In fact, we're going to have to work fairly hard to produce an extension that's not separable. Any extension that you can think of right now, I mean, unless you've gone delving into the notion of separability previously, you probably are not going to be able to come up with a separable extension. We'll have to actually do some work to produce such a thing. So we'll say it like this. So we will see that separability is, and I'll put this in quotes once more, it's common. Yeah, we'll have to do some hard work to actually produce an inseparable extension. Okay, so suppose, now, so that's sort of the end of that. Okay, so now suppose that L over K is separable, and that we've got this field in between K and L. So, all right, so we've got M sitting in between K and L. Oh, and one more thing. Let's take alpha. Where do I want alpha? In L. Alpha in L. So, what we saw a second ago in this observation part 2 right here, we saw that if you have a field in between K and L, then the extension M over K is separable. There's the question now, what about L over M? Separable or not? Now, what I want to do, all right, so we chose this alpha. So I want to look at the minimal polynomials now. So let's consider and I'm going to have to use double subscripting now. So M sub alpha K and M sub alpha capital M, right? So these are the minimal polynomials for alpha with respect to both K and M. So now, if we look at these polynomials, if we look at M sub alpha K, so let's say viewing M sub alpha K, well, okay, all the coefficients, all the coefficients, since they're from K, they have to live at M, so we can view M alpha K in M bracket X. And when we do so, what we should notice, so we have the M alpha k, oh, actually it's the other way around, m alpha m divides m alpha k. Why is that? Because m alpha k is a polynomial for which alpha is a root. If it's living in here, that means that it has to be in the ideal generated by m sub alpha m, right? Which means it's got to be a multiple of m sub alpha m. So since L over K is separable, we know that m alpha k splits into distinct linear factors in the splitting field. So since m or lk is separable, m alpha k is equal to, and let's just write it out, so it'll be x minus alpha. Actually, let me use a different symbol. How about beta 1 up through x minus beta sub n, where each beta I is in sigma, and I'm just going to use sigma. That's our standard symbol for the splitting field, so I don't want to have to write every time where sigma is the splitting field. Okay, now, all right, fine. So we know what m sub alpha k looks like, and we also know that m sub alpha m divides m sub alpha k. Which means, and the reason for this is that sigma bracket x is a UFD, so when we factor, it's always going to be unique. That is going to tell us exactly what m sub alpha m has to look like, right? So, oh, and I guess, yeah, where each I need to say distinct here, where each beta I in sigma is distinct. So, since sigma bracket x is a UFD, we have up to reordering that m sub alpha capital M is going to look like, well, it's going to look like some of the factors here, and so we might as well assume up to reordering that it's the first, the first few of them. So m sub alpha M equals x minus beta 1 up through x minus beta R, right, for some choice of R. Okay, so what does that tell us then? Well, so the minimal polynomial for alpha over m splits as a product of distinct linear factors, which means that this polynomial is separable over m, which means that alpha is separable over m. And remember, alpha was chosen in m, so therefore, alpha in L is separable over m, and conclusion, conclusion is, oh, in fact, let's write this, I want to write this as a theorem that collects both observation 2 and this discussion that we just had all in one place. So let's say it like this: we have proved and so this will be theorem 4.1. Is that chapter 4, right? If L over K is separable, and we have a field in between, then both M over K and L over M are separable. Okay, so now the question arises, why do we care? Right? What's important about this? I mean, I think normality, it should be clear why we care, because it tells us, it's essentially another way of saying we're working with a splitting field, right? But now separability, right? Why do we care about distinct roots? So here's just, I mean, we're going to see this as we go. Separability is useful for counting. And so at some point soon, we're going to start doing Galois theory, right? We're putting all the pieces together. And at some point, we're going to have groups involved, right? And we're going to need to be able to count. We're going to need to be able to know the size of the group, right? And so separability, when we know that we have a separable extension, it's going to allow us to with confidence, know the size of a particular group. Okay, so let's see how that goes. All right, and we'll have a number of theorems, and they're essentially all going to be counting theorems. So first, theorem 4.2. So let's say, right, okay, so let's let K adjoin alpha over K be algebraic, which is just another way of saying alpha is algebraic. Alpha is an algebraic element. And with the degree of K adjoin alpha, sorry, so now we know it's finite, so it's going to equal some number D. Oh, and I also need a monomorphism. Let's say, and let I from K into L be a monomorphism. So what's happening here? What we really had was we have K sitting inside L, basically, right? And then alpha lives in here, and we join alpha to K. So if if alpha is separable over K, and then we want to look at the minimal polynomial, or the inclusion or the injection of that. So and I of M alpha splits over L, then there exists exactly, so there exists D then there exist D extensions let's say extensions K adjoin alpha to L of I. So we've had a number of extension theorems, and now, but they've never told us how many. This now tells us how many we have. I mean, I guess in a way we had some sense, right, that for each root of I of M of alpha, we got another extension. And so now you can see why separability might be important. If you have distinct roots, right, then you know exactly how many extensions you have. Okay, so for the proof, and this goes back, so like I said, we do have a sense of how many extensions they are from a previous theorem. In fact, this was from corollary 2.6. So by corollary 2.6, the number of extensions of capital I to monomorphisms K adjoin alpha into L equals, well, it equals the number of distinct, oh, let's give that a name actually, the number, a symbol. So the number, let's say capital, or not capital S, little s, of distinct roots of I of m sub alpha that lie in capital L. Right? How does that work? Well, for each of the roots of I of m alpha, that would correspond to what we call beta. There's an extension I that takes alpha to beta. Remember that? Okay, so we just want to make that statement precise now. And it'll just, the separability is what's going to guarantee that we can actually count it. So since D, well, okay, so that's the degree of the minimal polynomial, which is the degree of k adjoint alpha over k. Sorry, I didn't even want to say that. I want to say that's equal to the degree of I of m of alpha. That's what I need. Right, our monomorphism does not change the degree of the polynomial. We have S less than or equal to D. And, oops, so what are we saying here? The number of distinct roots is bounded by the degree of the polynomial, right? Because you have at most, and I should say it this way, the number of roots is bounded by D. The number of distinct roots then is going to be less than or equal to D. So we can say and S equals D if and only if our I of m alpha splits into distinct linear factors in L. Now, since alpha is separable over k, and I of m alpha, I gotta say this carefully here, and I is a monomorphism. I of m sub alpha is separable over, over I of k, which is sitting inside L, if you want to get technical. So what's happening here, a monomorphism preserves separability, right? Because if you had distinct roots here, if this factored, if I of m alpha factored in such a way that you had repeated roots, that would lead to a factorization of m sub alpha that had repeated factors. I think I said repeated roots. I should have said repeated factors. So what does that mean then? All right, so what are we saying here? That is I of m alpha splits into S distinct linear factors. Over L. Okay, over L. Right, so it's this part right here, right, that we get from the separability. Okay, now I want to prove a more general theorem. It almost feels like corollary to our previous theorem, but it's not quite. So this is theorem 4.3, and it essentially generalizes theorem 4.2, but it makes full use of the results of theorem 4.2 in the proof. So here we go. So let's let the degree of k prime over k equal some number d, and let I from k to L be a monomorphism. So once again, this is going to be an extension, but it's going to be an extension counting theorem. So monomorphism. If k prime over k is separable, and I of m sub alpha splits over L, splits over L for every alpha in L. Oh, sorry, no, not in L, every L in K prime. Then there are exactly d extensions from k prime into L of I. Otherwise, there are strictly fewer. So otherwise, there are less than d extensions. Now the proof is actually induction on the degree, so on this number d. Induction on d. So for the base case, so if d equals 1, what does that mean? Well, it means then that k prime is equal to k. So then k prime is equal to k. And so if you try to extend I, there's exactly one extension, right? Just I itself. So and so we can say and there is exactly one extension of I. Who is that? Well, it's I itself. Yeah, there's nowhere to extend to. Okay, so there's the base case, and so now, so let's set up our inductive hypothesis now. So assume the result holds for degree strictly less than d, and suppose that we're working now in dimension d, in degree d. And here, let's be degree d greater than 1. Now, I don't know if case 1 and case 2 is right. What I want to do is I want to prove that when these hypotheses are satisfied, all right, so we've got separable and that it splits over L for every alpha, then I want to prove the exactly d extensions part. I also want to prove that when the hypotheses are not satisfied, there's less than d extensions. So I'm going to consider the two cases. I'm going to write them as case 1 and case 2. So case 1, right, so let's assume that k prime over k is separable, and that I of the minimal polynomial splits, I m alpha splits over L for every alpha in k prime. I'm down to my last piece of chalk. Okay, so now I'm just going to pick. Now we know here that the degree is strictly greater than 1, which means that k prime is not equal to k, so I'm going to pick somebody in k prime, not in k. So let's pick alpha in k prime minus k. Now what we know is by 4.2, so theorem 4.2, there are there are exactly degree of k adjoint alpha over k extensions k adjoint alpha to L of little I. So let's just pick one of them. And here's the idea. Remember, we're trying to do induction, right? And we assume that it works when the degree is strictly less. So this is going to sort of bootstrap us up so that we'll be able to apply the inductive hypothesis. So let's fix one such extension, call it little j. Now, since the degree of k adjoint alpha over k has to be greater than 1, because alpha does not live in k, so this is strictly k is strictly contained in k adjoint alpha, right? Because alpha is not in k. Oh, so we have that the degree of k prime over k adjoint alpha has to be strictly less than d. So you can see we're trying to set it up so that we can apply induction. So now what do I need to do to apply the inductive hypothesis? I need to show that I of the minimal polynomial splits over L. But it's the minimal polynomial with respect to k adjoint alpha, right? So to apply the inductive hypothesis, we must show that I of the minimal polynomial of alpha relative to k adjoint alpha splits over L for every, say, little beta in, did I say something stupid here? Oh, yeah. I don't want to use alpha twice. Sorry. I need, it's going to be every element, but I can't reuse alpha. I need to call that I, or m sub beta, k adjoint alpha for every beta in k prime. So let's do that. Let's pick beta in k prime. Then in k adjoint alpha bracket x, right? So we're going to be working with polynomials whose coefficients are in k adjoint alpha. we have that the minimal polynomial of beta with respect to k adjoint alpha divides the minimal polynomial of beta relative to k. Right? I mean, if you expand the number of coefficients, the coefficient field, right, the degree of the minimal polynomial can go down, right? So it's got to divide. So it follows that in L bracket x, J of the minimal polynomial of beta with respect to k adjoint alpha divides J of the minimal polynomial of beta with respect to k. But now since we're using coefficients in k and j is an extension of I, this is exactly equal to I of m beta k. Now, we assumed, right, that for every alpha or beta, this guy splits. Right, so let me clean this up a little bit. So what this means, though, this splits over L, which tells us that this one splits over L. So let's say it like this. So since I of m beta k splits over L, so does J of m beta k alpha, right, because it divides. This one divides that one. Okay. So now we can apply our inductive hypothesis. So by the inductive hypothesis, there exists k bracket k prime over k adjoint alpha extensions of J, and of course each one of those is, if it's an extension of J and J is an extension of I, then the extension of J is an extension of I. So in fact, let's say that in parentheses. So and each is an extension of little I. Okay, so now we have, okay, so what do we have? We have, well, we have this many extensions of I. So now we have k prime over k adjoint alpha times k alpha over k extensions of I. All right, and that's exactly what we need. Okay, so now in the second case, when things fail, so case 2, so suppose there exists some say alpha in k prime such that I of m alpha has less than k adjoint alpha over k distinct roots. living in L, of course. So then, by our previous theorem, so by theorem 4.2, there are strictly less than k adjoint alpha over k extensions of I, and then you just throw the Tower law at it. So by induction, each extension, so by induction, each of these extensions, so each extension has less than or equal to k prime over k adjoint alpha extensions. And so now Tower law says that we will have, so Tower law, there are less than k prime over k adjoint alpha times k adjoint alpha over k extensions of capital I. Okay. All right, so that completes the proof, and that's enough for today, so we'll see you next time.